Welcome back to the Tucsen Mastering Scientific Cameras course. This is part 2, Gathering Photons, and in this part we're going to be having a look at the process of actually collecting photons with our pixels. And there's two really important factors that go into this: the quantum efficiency, which is the efficiency by which we convert photons into detected photoelectrons, and the pixel size, the physical area of our pixel, which determines as well how much photons it can collect. But first, really exploring what an actual pixel is and what the structure of it is, because this will help us understand some of the concepts later on. Of course, cameras are formed of a two-dimensional grid of square pixels. Some cameras are one-dimensional, but most are two. And if we zoom in on a side-on view of what these pixels look like, we've got two different designs shown in this diagram to the right-hand side. On the left, we've got what we call a front illuminated pixel, and on the right, a back illuminated pixel. We'll drill down into what the differences between these are in a moment. The most important bit is the light-sensitive silicon, which is in pink on this diagram. And you can see photons in green coming in from our optical system, which is above the camera, out the top of the screen in this case of this diagram. And these photons in green are coming through, and they're successfully being collected by that pink silicon substrate, where that process of a photon being converted into a photoelectron, and that representing the detection of that photon, happens. That's where that happens. We do have to have some degree of control over this process to actually turn some silicon into a camera. And that means that we have to put wiring on top of the silicon. At the very least, it needs to be next to the light receiving surface. So this leads to, in the front illuminated pixels that you can see on the left, the wiring is on top of that silicon, and it will block some of the photons coming in. They might be absorbed by the wiring, or more likely they might reflect off the metallic wiring. So that's not quite so ideal for capturing our photons successfully within the silicon substrate, but it has to be there to control the sensor. And for front illumination, that is the way around that the sensor is designed, with the wiring above the light detected area. Fortunately, on front illuminated sensors, we can use micro lenses, tiny lenses on top of each and every pixel, which can funnel photons past the electronics and direct them successfully into the silicon substrate. And actually, these micro lenses can be really quite effective for steering light past the wiring and really minimizing the influence of that wiring on our light detecting efficiency. However, there's another sensor design which we can see on the right, and that's called back illumination. And in back illumination, we directly flip this geometry around, and photons just hit light sensitive silicon, and there's nothing really in the way. And this is obviously a more sensitive way to make a camera. We can more successfully collect photons more of the time. However, it does come at a cost. We actually have, in the front illuminated case, a much thicker layer of silicon than just the light sensitive area. You know, the silicon substrate could be a millimeter or so thick to support the sensor on top of it. But only the top, around 1.1 micrometers, is actually sensitive to light. And with the back illuminated case, we can't have any of that supporting silicon. We'd need to have just that 1.1 micrometers so the wiring can be right next to it and manage the sensor and move charges around and measure them. So with back illuminated sensors, we need to thin the silicon right down to precisely 1.1 micrometers. And that's an expensive process. So typically back illuminated sensors are far more expensive, and the cameras made with them are far more expensive than front illuminated sensors. So what's the primary difference between these sensor designs? Well, primarily it's quantum efficiency, this efficiency with which we collect photons from our imaging subject. quantum efficiency is actually wavelength dependent due to the materials within the camera pixels and within the camera sensor and the actual properties of silicon itself. There's a wavelength dependence to how effectively it can collect light. So if we ask the question, if 100 photons hit a pixel, how many will be detected as photoelectrons? We need to express this as a graph with wavelength on the x-axis, and then the number of photons, if we've got 100, or the percentage of photons that we'd collect on the y-axis. And you can see here a comparison between back-illuminated sensors and front-illuminated sensors. Both of these sensors peak around 600 nanometers wavelength, sort of roughly in the green area of the spectrum. And in both cases, we have tailing off to either side. In general, back-illuminated sensors do offer the highest quantum efficiency. We can see here that we reach almost 100%, 95% of photons being collected in the case of this back-illuminated sensor. So it's doing a very good job of collecting photons. But the front-illuminated sensor is also doing a very good job. Depending on your application, this difference between 90 to 95% peak quantum efficiency for the back and 82% for the front, that might be significant, but for many that might not. 82% efficiency might be plenty for many applications. It really depends on what you're doing as to whether this is a significant difference. But yes, modern front-illuminated sensors aren't far off the back-illuminated sensors in their quantum efficiency. So the next important factor is the pixel size. To understand this, let's think of an analogy where we're trying to collect rainwater, where rainwater, of course, represents our photons coming in. You can probably imagine that a bucket is going to be more effective at this than a cup. The wider area of the bucket is going to collect more raindrops than the smaller cup. The analogy holds out for camera pixels. Generally, the larger the camera pixel, the more light you can collect, and therefore the more sensitive the camera. And it's the area of the camera pixel that is the important quantity. So if we have a camera pixel where we see on a specification sheet that the pixels are a certain size, that's the XY size of the pixel, not the area. So a 2 times larger pixel size will have a 4 times larger area and capture 4 times more light. If we look at some example common camera pixel sizes, if we have a 2.4 micrometer pixel, that's got an area of around 6 square micrometers. But if we compare that to another common pixel size, a 6.5 micrometer pixel, then we have 42 square micrometers of area, around 7 times larger area, and are capturing around 7 times more light. If we then go up to another common pixel size, 11 micrometer pixels, we're now at 121 square micrometers in area, around 3 times that of the 6.5 and around 20 times that of the 2.4. So we're talking very, very significant differences in sensitivity here. And the reason that we have a different sensitivity is, of course, that we're increasing the amount of photons that we collect without actually affecting the noise with which we measure those photons. That's why pixel size increases lead to sensitivity increases. Overall, the same number of photons might be hitting the sensor, but if they're collected by larger pixels and fewer pixels, then overall our signal to noise is going to be better. However, it's not necessarily the pixel size on the actual camera sensor itself which matters. We need to take into account the magnification of our optical system. And this leads me to what we'll call the imaging pixel size. And this is what we might call the size of pixels in image space, i.e. after the magnification is applied. This is the pixel size of the actual digital image that you'll look at on the monitor. It's like if you're measuring distances on your imaging subject and you've got a scale bar up, how big is that pixel? How big is that scale bar? This is the most important quantity, not the size of the pixel on the sensor necessarily, but the size after you've applied your total magnification of your system. So say we have an 11 micrometer pixel on the camera sensor. If we use that with a 100 times microscope objective, then we're effectively dividing that pixel size by 100. And in our image that we get on the camera, we're looking at 110 nanometer imaging pixel. And that's the important number to compare to other optical setups to work out the sensitivity based on pixel size. So the pixel size in image space is simply the pixel size on the sensor divided by the total magnification of our system. So in terms of this sensitivity increase that I've been talking about with larger pixels, we'd achieve the same thing whether we increase the actual pixel size on the sensor or decrease the magnification that we're using. It achieves exactly the same thing. But for the same magnification, e.g. the 60 times microscope objective or a lens at a set focal length and a set distance from your subject, larger camera pixels will be more sensitive. So if you're just directly swapping out a camera on the same optical setup, you can increase sensitivity with larger pixels. Moving the subject further away or decreasing the focal length if you're using lenses and having that object then take up fewer of your camera pixels, have its light concentrated on fewer camera pixels, effectively increases the pixel size and can increase your sensitivity. The same effect will be seen with using a lower magnification objective on microscope or using additional optics after the microscope objective to change and maybe decrease the total magnification of the system. These increase imaging pixel size. We can also do binning, where we group pixels into, for example, with 2x2 binning, we have 2x2 groups of pixels and decrease the effective pixel count of our camera by a factor of 4, but increase our effective pixel area by a factor of 4. And we sum up the contributions of each of those pixels. This can effectively increase the pixel size in a very significant way. However, with modern cameras, with CMOS cameras, this does come at a slight noise cost. But typically, the benefit of binning in terms of sensitivity and capturing more photons in our now larger pixels will offset that cost in noise significantly. And it's still a powerful way to increase the sensitivity of cameras. However, all of this talk of increasing pixel size to increase sensitivity does, of course, come at a trade-off. There's a significant trade-off that we need to consider depending on how important resolving fine details is in our image. We're going to be talking about that in the next part of this course, but remember that we can't just keep increasing pixel size forever. There is some limit that we must brush up against, but up until that limit, increasing pixel size is a significant way to increase sensitivity. So, in summary, first of all, we looked at quantum efficiency, which is this question of how likely is a photon to be collected. This is, of course, wavelength dependent. Back illuminated sensors, where photons just directly hit the silicon with nothing in the way, can have around 95% peak quantum efficiencies, collect almost every photon that hits them. However, they do come at a higher cost, so cameras that are back illuminated are likely to be much more expensive. Front illuminated cameras are much easier to manufacture, and so they have a lower cost, and they can still reach really high quantum efficiencies, around 82%. Whether that difference between the 95 and the 82 is significant will come down to your application. Certainly for some it will be. Next we looked at pixel size, and here the pixel area determines the light collection ability of the camera. 2 times bigger pixels will collect 4 times bigger light, but it's the imaging pixel size that really counts. That pixel size after the magnification of our system is applied in image space. And pixel size is a trade-off. And again, we'll look at that in detail in part 3 of this course. But before we do that, we're just going to briefly look at some application examples. First of all, there's this question of when do we need quantum efficiency? When is it important in our applications to have high quantum efficiency? And the answer is certainly not in all applications. But this is something that you'll need to think about for your application and consider, do you need high quantum efficiency? To explore a couple of examples of when it might be beneficial to have high quantum efficiency, one is low light applications where, for example, we might be doing biological imaging and then biological samples can be damaged by high light levels, and we also might be using fluorescent dyes which can photo bleach over time. The more light we put on them, the more we change or effectively destroy the fluorescent molecules that are sending light back to us. So we want to minimize the amount of light that we need to shine on our sample. The example of this is live cell imaging. If we can increase the efficiency with which we collect light back from the sample, we don't need to shine as much light onto it in the first place. So for live cell imaging, that difference in quantum efficiency between front and back illumination, for example, can be very significant, and we can really benefit from having high quantum efficiency cameras. Another application where it can be very useful is when we're trying to have a minimum exposure time in order to move through a large quantity of samples very quickly. And then we're trying to increase our quantum efficiency to collect the same good high signal in a shorter time period by having a more efficient collection process. High content imaging is a very common example of this, where we really are trying to move through a large amount of data quickly. We've got many images to acquire, and we want to minimize the exposure time to minimize the total duration of that experiment and move on to the next sample more quickly. Another time when we might want to lower the exposure time by collecting light more efficiently is if we're trying to capture changes in our sample from one frame to the next, capturing dynamics and moving things within our sample, or just other changes within our sample, like in stochastic super resolution imaging. We also might have applications where we're tracking the movement of something, as in single molecule tracking. But in both of these cases, a shorter exposure time means we're capturing with better temporal resolution, and we're seeing more of what's happening. We also might be, similar to point number 2, changing multiple parameters, or trying to acquire a large volume of data in X, Y, and Z as fast as possible. That might be the case in spinning disk confocal microscopy, in light sheet microscopy, or in structured illumination microscopy. You might also come across cases where your experiment requires detection of very low signals. We're talking a number of photons that you could count on one hand. Single molecule imaging might be a case of this. And in this case, of course, every bit of detection efficiency that we can get will help us have a higher confidence of detecting a signal and be more confident that a signal is really a signal and not noise. The final time when high quantum efficiency might be useful is if we're working in the ultraviolet or in the infrared, where quantum efficiency of silicon sensors can be quite low. So if we have a high quantum efficiency camera, especially a back illuminated camera, it's more likely to have decent quantum efficiency to work with in these more extreme regions of the wavelength spectrum. But we do have to ask the question, how many photoelectrons do you actually need? Because higher quantum efficiency is ultimately about capturing more photoelectrons. More captured photoelectrons means higher image quality through better signal-to-noise ratio. But does your imaging application actually need higher image quality? Do you need a higher signal-to-noise ratio? It might well be that for your imaging application, you're already at a level where any further increase would be undetectable, or at least have no meaningful impact on the image's ability to answer your scientific questions, which is ultimately what we're all about in creating scientific images. We're trying to answer specific scientific questions. And it may be the case that capturing more photoelectrons, that successfully capturing more photons and turning them into photoelectrons won't actually lead to any additional benefit for your scientific questions. So the question is, does your image need to be higher quality? And of course, this is one that only you can answer with your particular imaging application. It might well be that it will be absolutely essential and really beneficial to your imaging to have a higher quantum efficiency and capture more photoelectrons, but we still have to ask the question. For example, if you're collecting 1000 photons per pixel, a 75% quantum efficiency would convert those into 750 electrons, versus 95% quantum efficiency, like we would get in a back-illuminated camera, would give 950. Will you actually notice that difference? The signal-to-noise ratio is already very high. It's high enough that this image would look very high quality by eye, and we might not be able to detect that change in signal-to-noise ratio by eye. Some analysis routines would be able to pick it up, and it might be meaningful for some applications, but we're probably not going to be able to see that difference. However, if on the other hand you're only collecting 100 photons per pixel, conversion of 75 photoelectrons or 95 photoelectrons for our two different quantum efficiency cases would now be much more noticeable, because it has a larger impact on our signal-to-noise ratio because we're that bit closer to the noise with this lower signal. So here it might well be beneficial for a majority of applications to have that higher quantum efficiency. But again, it entirely depends on what your application is and whether you actually need that additional signal-to-noise ratio and that additional signal. But finally, what might be some cases where high quantum efficiency is typically not needed? When do you not really need to think about this? In general, applications where you can control the light level, how much light you shine on your subject, you're not really having to worry about high quantum efficiency. Typical examples might include bright field or phase contrast imaging, where you can simply turn up the bright field lamp and it can go way higher than you even need it to be. In that case, higher quantum efficiency will serve no purpose for you, basically. Another case is inspection imaging, where again we will typically have control over light levels. This won't be the case in all cases for either of these applications, but typically that might be some applications where you don't need high quantum efficiency. Otherwise, and similarly, applications where you can increase the exposure time without any major drawbacks for your imaging workflow. If you can go from, say, a 400 millisecond exposure to a 500 millisecond exposure, or even a 3 millisecond to a 4 millisecond exposure, you're going to have a significant increase in the amount of photons that you can collect. And for many applications, that's not going to be much of a hardship to increase exposure in that way. And ultimately, a thing to remember is that many camera users do overspend in order to achieve a nice high quantum efficiency that their application didn't actually necessarily need. This is something to bear in mind when considering different camera options.